Good morning, everyone. So today I am going to present on the topic of micromechanical and microstructure analysis of lunar concrete. So this research is produced under the Clarkson University and under the guidance of Professor Robert Thomas. So I'll proceed with the presentation. So basically, this presentation talks about NASA. NASA is planning to send send 3 people on Moon by 2025, and afterwards is planning to build some kind of a sustainable construction on Moon. And this project, it deals with the same thing which covers the sustainable construction on Moon, where things like launching pads and other stuff, where NASA can build those stuff considering the in-situ resource utilization. So in-situ resource utilization is like using the same material which is present on Moon and utilizing it for building specific structures on Moon. In my research, I used a geopolymer for this same purpose. So within the geopolymer, I have an aluminosilicate material, which the lunar regolith, which is already present on Moon, it already has the silicate property. Then I have an alkaline activator, which is the lunar soil, which it typically contains all the extractable soil and alkalis, which combined with the precursor produce the geopolymer, which will be tested upon for the further testing in my upcoming slide. So within this specific geopolymer, I use the precursor in the form of like a lunar regolith, which is off-planet research lunar highlands. So this specific lunar regolith, it covers the area and it represents lunar highlands, which covers the 60% area of the Moon, and the other 40% is the lunar mare region. The composition of OPRH2N is 70% unorthosis, 30% basaltic cinder. These shows the images of the lunar regolith, which is the simulant. So basically, why we are using the simulant, because when NASA went to Moon on 1970s during their Apollo missions, those samples they brought, those are like very scarce, and it's like it would be improbable to use them for the large scale testing. So considering that, within my research, I am using the specific geopolymer and trying to test them in a micromechanical situation where I'll be able to determine their micromechanical properties out of it. So the objectives of my research is optimize the mixture composition of lunar geopolymer concrete considering 3 parameters, which is the solution to simulant ratio, silica modulus, the curing temperature. So I am using these 3 parameters to determine the compressive strength of how my geopolymer would perform. Then characterizing the microstructural and the micromechanical properties of lunar geopolymer concrete using the nanoindentation analysis technique. And finally, compare the properties of lunar geopolymers and simulants to the terrestrial cement hydrates and aggregates. So, talking about the methodology, so as I already mentioned, like we are going to use the central composite design methodology to composite the specific geopolymers. We have 3 parameters: solution to simulant ratio, silica modulus, and the curing temperature. And the specific ranges within the central composite design, which uses a method where different parameters they help determine a specific response variable for me, which is the compressive strength. So this tells the ranges, which is 0.35 to 0.55 for solution to simulant ratio. For silica modulus, it is 0.5 to 3, and for the curing temperature, it is 55 to 95 degrees centigrade. This on my right side, it shows the OPRH2N composition, which is my lunar regolith, which has been used as a precursor for the geopolymer. It shows plagioclase has the composition weightage percentage of 70.4%, amorphous class is 26.5%, and olivine has 3.1%. All of these are rare elements, which apart from it, the OPRH2N specifically, it is a kind of a lunar simulant which has been produced by off-planet research, which is very like a high-performing simulant. So that's the consideration while considering using this specific lunar geopolymer simulant. This tells the central composite design methodology. First we have the response parameter, which I already mentioned, which is the result of the 3 parameters which I have already mentioned, and it gives me the ranges of 6 to 37 megapascal. So what I did was like these testing was performed in Penn State University using some miniature cylinders, and all of these central composite design compositions, they resulted in 20 miniature samples. And afterwards, they were tested for the compressive strength testing, and I got these ranges for the strength, which was 6 to 37 megapascal. On right side, I have this pictorial diagram, which shows the 3 major components, which is the silica modulus, temperature, and solution to simulant, and shows like what are my design parameters while considering for my response parameter, compressive strength, how these would perform considering all of these three specific parameters. So my other methodology is about nanoindentation. So what nanoindentation does is like it pieces within a specific material and tries to determine the specific properties, which are the micromechanical properties, considering the unloading curve of the displacement. So when the material would pace within it, it would displace some mass, and considering that specific displacement, I'll be able to get two properties, which is the hardness and the elastic modulus. And these hardness and elastic modulus properties are like the result of the specific load applied, the contact area, and the stiffness of the sample. So this shows the microstructure phases deconvolution, like how the microstructure results in the phases when indented upon. All of these small boxes from the top left corner to the top bottom right corner shows all those indents which have been performed on the specific area of the microstructure of the geopolymer. As you can see, the deconvolution shows that the red area, which corresponds to the olivine, which is the hardest material within all of this microstructure. The green area, it represents NASH and Castiel, and the blue area, it represents the plagioclase and the amorphous class. So, my nanoindentation results talks about how I have been able to determine the phases. So I had four phases, which was like divided into two major phases, which was hydrated portion phases and the unhydrated portion phases. In the hydrated portion phases, I had NASH and Castiel. In the unhydrated portion phases, I had amorphous class and plagioclase as one phase, and then olivine as another phase. So as you can see within the microstructure, and these are the micromechanical maps, which shows the range of the hardness range, which is from 0 to 16 GPa for the hardness, and for the reduced modulus, it is 0 to 200 GPa. The highest hardness as depicted by the microstructure, and then comparing them with the mechanical maps, shows olivine has the highest hardness and highest reduced modulus. So this shows the statistical analysis results. So basically what I did was, like, after getting all of those results, I used a specific Gaussian mixture modeling, probability distribution, and then utilizing it, comparing it with the machine learning technique, which is the clustering, I was able to determine like how these phases were like specifically designated to those specific materials within the microstructure. So within this deconvolution, as you can see, the red and the blue clusters, they represent NASH and Castiel. And the green and the black phases, they represent the plagioclase and amorphous class and olivine respectively. So the GMM, basically what it does is like, when considering the clustering technique, it doesn't like specifically tells like, okay, these are the specific values which match the specific phases. It gives us kind of a prediction. This can be the phases present within the specific microstructure. Again, this shows the statistical analysis result where I have applied a threshold while determining those two phases of hydrated portion phases and the unhydrated portion phases. For the hydrated portion phases, I had the reduced modulus range from 0 to 40 GPa, and for the hardness of 0 to 2 GPa. Above and beyond these specific parameters, all of the other phases were classified on the basis of unhydrated portion phases. As you can see, one is the plagioclase and the other one is the olivine in the unhydrated portion phases. So now going to the literature review, how my specific phases, they compare with what has already been mentioned within the literature. So as you can see in the Castiel, my results, what they produced was a range for the reduced modulus of 7.9 to 19.5 gigapascal. And in literature, we had the values of 4 to 20 gigapascals. And similarly, for the micro hardness, I had 0.30 to 0.78 gigapascals. And in literature, it was 0.11 to 0.75 GPa. As you can see in the all other three phases, there is also the same kind of a comparative threshold which they are trying to occupy within. It's not like there are some extremities where they are increasing much more than what has been already represented within the literature. As you can see in olivine, for the reduced modulus, the value goes a bit higher in my case as compared to the research literature, where it goes up to 169 gigapascal. This shows the specific model of like my compressive strength, how it resulted considering all the three parameters. So I used a stepwise regression model, and how this compressive strength is proportional to all of those three parameters and their interaction terms. As you can see, the S to S, which is solution to simulant ratio, is indirectly proportional to the compressive strength. Similarly, temperature is also indirectly proportional to the compressive strength, and silica modulus is directly proportional to the compressive strength. This is the solution to simulant and silica modulus. They are statistically valid because, as you can see, the p-value is respectively closer to 0.05 threshold. And the overall value, p-value of the model was 0.0011, which again is within the specific threshold of the p-value. So now, leading up to the conclusion, the compressive strength of lunar concrete is indirectly related to the solution to simulant ratio and the curing temperature, and directly related to silica modulus, as shown in the previous slide. The lunar concrete includes 4 microstructural phases: NASH gel, cast gel, glass and plagioclase, and olivine, in increasing order of hardness and reduced modulus. The hardness and reduced modulus values for all the identified phases align well with those reported within the literature. And finally, the lunar regolith-based geopolymers should exhibit similar micromechanical properties to terrestrial geopolymers, at least when cured at standard pressure and gravity, which was in my case. So thank you everyone. If you have any questions, please proceed with.